Good. Thank you for the introduction. I will talk about a new-ish specimen, which we called a 4O SLB, which basically stands for out-of-plane loaded single leg bending under 4-point bending. And to give you a short summary of what I will talk about, I will give an introduction, then I go a little bit into the theory of this specimen. I will show our setup we used and the results we obtained and give a little bit of an outlook and summary. Now to the introduction. If you Google after mode 3 tests and look for them, there aren't that many that are widely used, so it's still an open field. One interesting test, however, that was published 2006 was this one, which was called a 4ENF test. It's a mode 3 test. It was conducted on wooden specimens. And if you think about it a little bit, these two outer arms, they shear off in this kind of way from the middle arm. So you get some kind of mode 3 separation in this setup. And we wanted to look if this setup was applicable to the testing of structural adhesive joints. And to this end, we changed the geometry a little bit. We got rid of the second short beam because the manufacture of this is quite difficult if you have 2 adhesive layers and 3 beams. And the drawbacks we get by this asymmetrical setup are quite small, so we settled for this setup. However, if you look at this setup, you will notice that you cannot see the crack tip, which you might think is a big problem, but you will later see that it's not a problem at all. And if you want to obtain R-curves, there are ways to infer the crack length, which I will show. But now to the theoretical background. You can think of this setup like a beam, which has just a jump in the stiffness, where the stiffness increases by a factor of 2, where the right part is just the part of the beam which is still intact, which hasn't cracked yet. And if you then use these assumptions and do your calculations, and for the case where your loading conditions are perfectly centered, so you have ideal 4-point bending, your energy release rate does not depend on A. So you don't need the crack length to obtain measurements for the critical energy release rate. So if you're only interested in that, measuring the crack is no problem at all. We also think that the J integral may be useful, may be used here. This kind of geometry violates some conditions that need to be applied present for the J integral, but we still think that this equation should hold for the specimen. So you can use this as well. Now to the setup, we just used the servo-hydraulic testing machine. The setup is depicted here. We have the 2 supports, left and right. We have the seesaw in the middle for the 4-point bending. So you can see it's quite simple and neat test setup. It's nothing complicated. In the foreground, you can see part of the DSC system, which we use to infer the crack length. And for the DSC, you have actually 2 choices where you can place your beam. You can place the front beam in front of the camera, the long beam, or the short beam. The strains then can be measured at the top and the bottom green lines and the deflections at the center line. However, we, with our geometry and our setup, had one problem with DSC. We conducted the tests with the Seeker Power 498 adhesive, which is quite strong. So our specimens were quite large. Like this seesaw has a span of 300 millimeters. So the measurement window was quite large and the spatial resolution of the DSC system wasn't good. So our measurements for the DSC aren't that good. And because of this, we also use the optical fiber methods, which you already heard twice now. We just glued it in the colored sections where you see here. This is a bottom-up view of the specimen, basically. So it was a backface strain measurement. And the results we get, I will show you now a small animation. I want you to focus on the colored regions in the left plot. And as the strain rises, you will see some kind of step in the strains that will propagate to the left and to the right. And that's also the way where how you can infer the crack length. If you look at it now, you see the step rise. And if the crack starts to propagate, this kind of step also moves. And this is what we will use. The program we did was split into 3 sets of tests. The first set was just a compliance calibration. The second set was used for R curves and cohesive laws, where the correct length was determined using DSE. And a third set, again, R curves and another compliance calibration, but this time using the optical fibers. Now to the results. For the compliance calibration, we did it with two methods. One method was the regular method, where you just manufacture a bunch of specimens with different initial track lengths, load them, and get your data. The second way, we used the fact that we couldn't measure the track length with the optical fiber and programmed the machine to execute a loop where it would load a specimen, unload again to a displacement of 10 millimeters. We took a strain measurement and then loaded it again, but this time the displacement was slightly higher by the 10th of a millimeter. You do this a few hundred times, and then you drive the crack through the specimen really carefully and get a whole bunch of measurements that way. And you can see then the green and the yellow orange line are both on one sample. So you get a whole bunch of measurements for your compliance, which are in of itself not that accurate. They scatter quite much, but the sheer amount of data you can generate this way with a single specimen yields in uncertainties that are similar to the classical method, which in itself has better results, but is way more work to actually do, because the blue line is 11 specimens, the green line 1. So it's quite a nice way to do it. The crack length measurement in itself, again, no line of sight exists, but if you think about it from a pure theoretical standpoint, the jump in the stiffness also results in a jump in the strains you can measure. And this kind of data, which we would expect and already saw in the short animation, you can manipulate in various ways to infer the crack position. And the measurements we got, here, the DSC measurements, as you can see, they are quite noisy, but still you can see this kind of jump in a factor of 2. So you can actually use this data, which you will see later on, but the measurements from the strain optical fibers are way nicer. You can see the step is not actually a step because we have the process zone in there, quite large one at that. It's a far more gradual decline. But you can then infer the crack length. You see the small dot. This is just on the right. You see just a convolution of this data with a step function. And this will give you this point in the middle, which is not actually the crack tip, but it's a point that has a constant offset of the crack tip. And you can detect this point reliably. So you can use this to obtain your R curves. And the crack length we obtained this way: on the left, the optical fiber, on the right, the DSC with different methods. Again, DSC more scattery, but both methods work. And the critical energy release rates we measured were all consistent with one another, regardless of the method, if you use J-Irvin-Keyes equation or Berry's method. So you can use whatever you like with the specimen pretty much. They are consistent with one another. The R curves we obtained also weren't much surprising for this adhesive. They were mostly flat and quite nice looking. And the cohesive laws, again, no surprises there. We measured the black line there, which aligns quite well with the MC-DCP test, which is also a mode 3 test. And the two other lines were mode 3 tests that had a slight mode 1 part, so their fracture energy was smaller, but overall consistent results. So to give you a summary and outlook, we think that this setup is actually quite promising. It has an easy setup. The execution is quite straightforward. And if you're only interested in the critical energy release rates, you do not need to bother with DSC measurements to measure the crack lengths. It's quite nice that way. But even if you want to measure your R curves, you can do it with DSC, you can do it with optical fibers. It is possible. It's just a little bit more work in the post-processing of the data. But we still think that further tests are appropriate. The main question, or one of the main questions, is just if we have smaller specimens with weaker adhesives, if in that case DSC is more appropriate, if it is better. are different evaluation methods for the crack length method, or the ones we presented probably can be refined in some way. So if you are interested, we have published the findings. It's open access, so you can read it easily. Thanks for your attention. Any questions?